Hey everyone, thanks for coming to the Grid Modernization panel in the Clean Tech Summit. It's really nice to be able to redo this panel. Unfortunately, the first time we were snowed out, and now I'm sure we're all facing the issues of coronavirus, and so hopefully everyone is, or people attending are healthy and safe and doing okay. And so I wanted to uh, open the conversation with an introduction of our panelists today, who I want to thank a lot for taking the time out of their schedule to discuss grid modernization issues with us. So they're Jenny Chen of the Nicholas Institute for Environmental Policy Solutions, and Gary Ratcliffe at ABB. And together they have quite an extensive experience on grid modernization issues, ranging from the technical and policy aspects of integrating higher shares of renewables on our grid. So I wanted to let actually both first Jenny and then Gary share a little bit about your background, current role, and one aspect about the energy transition that is currently capturing your attention and interest.
Yeah, sure. And thank you for the kind invitation to UNC and NOAA. Yes, so welcome to the quarantine edition of our webinar, and I hope everyone is well. I understand there are a lot of students on today's webinar, so as I mentioned my background, you'll see that it's definitely a very scenic route, and I've done a couple different things. So if anything, I'm probably exhibit A of someone who's probably explored a lot of different things, faced a lot of uncertainty, and still came out okay. At least I think I came out okay. but yeah, I think so just a little bit more about myself. I work at the Duke Nicholas Institute for Environmental Policy Solutions, which is an academic think tank, and we strive to connect academics with stakeholders and policymakers, especially in the environmental and clean energy space. Before joining the Nicholas Institute, I was with the Natural Resources Defense Council working on energy issues, particularly issues that came before the Federal Energy Regulatory Commission and sometimes it's the Department of Energy. And before that, I was a law clerk at the Federal Energy Regulatory Commission. I went to law school, and but prior to law school, I did another stint in grad school. I went and did a graduate degree in physics, and I was thinking about a very different career, being a professor, but I really felt like that wasn't for me. So so I hope that you'll get a lot from today's webinar and think about different career options. And I think we're talking more about that later. The other question that you asked about, Noah, was one aspect of the energy transition that we really focus on today. And what I really focus on is policy making, and in particular, the policy and coordination required to facilitate or to drive the clean energy transition. It's probably a very broad topic, but anyway, I'm probably cheating there. But yeah, policy and coordination are very important in this area. Thanks.
So I'll introduce myself. I'm Gary Rackliffe, and I'm Vice President of Market Development and Innovation for ABB Power Grids. I'm not sure if everybody on the webinar is familiar with ABB, but ABB Power Grids is headquartered in Zurich, and we're a large supplier to electric utilities of different technologies. In terms of my background, I've been with ABB a long time, since 1989. Had a number of different leadership roles around business management or business development, marketing, strategy, sales, and also line management. Fairly active in the industry overall. I'm chair of the leadership committee for the Utility Products and Systems Division of NEMA, which is the Electrical Manufacturers Association. I serve on two government department committees, Department of Commerce, Renewable Energy and Energy Efficiency Advisory Committee to the Secretary, and then also I'm on a Department of Energy Advisory Committee for Advanced Distribution Management Systems. Distributech, those of you who are familiar with that trade show and event and technical program, I'm on the advisory committee. And then also IEC, which is International Electrical Standards. I'm a member of the Systems Committee for Smart Energy and the U.S. Technical Advisor. And then I serve on some other boards, SEPA, which is the Smart Electric Power Alliance, the GridWise Alliance, Texas A&M Smart Grid Advisory Board, and locally I chair the board of the Research Triangle Clean Tech Cluster. And so Noah asked one thing that's keeping me busy these days, and I would say if I were to pick one thing, it's looking at the transition to clean energy and how can the grid address the two major contributors of carbon today, power generation. So to address that, how do we integrate renewable generation and clean energy in the grid? The other one, transportation. As we electrify transportation, how do we supply the power for that transportation through the grid? And in background, I have a bachelor's in engineering and a master's of engineering from Rensselaer Polytechnic Institute, and also have an MBA from Carnegie Mellon.
Great. Well, thank you both so much. And as we continue this conversation in the webinar today, I did want to remind participants that there is a Q&A feature. So if throughout the presentation you do have questions, there will be an opportunity for our panelists to answer them, and you can click on the Q&A button. And in some cases, we may be able to get to them as they come if they're clarification or something, or also there will be time at the end allocated to Q&A. I should also mention, for those of you who may not know me as well, I'm Noah Kittner, and I'm assistant professor in environmental sciences and engineering at UNC, and also affiliated with the Environment, Ecology, and Energy program. So to kind of kick off this discussion, there's the grid, grid modernization to a lot of people can mean very different things. So I wanted to ask both of you to speak a little bit broadly about what does a modern clean grid mean to you, and how does that fit with your current work?
Should I start?
Sure.
Okay. Yeah, I think the grid is here because it's intended to serve customers and communities. So when we think about an achievable ideal, a clean grid includes a grid that helps bring greater convenience to customers, whether or not they're at home or on the road. So for example, today, folks might be sitting on the road commuting in traffic jams, and they have to focus on driving and staying safe. And that's not something that we have to, that's not a given. We don't have to have a situation like that in the future grid where we're thinking about automated vehicles, where these vehicles could be like more smartly driven and coordinated so that they're driven at a speed that avoids traffic jams or avoids congested areas. And you don't have to be a slave to your commute. You can do your work, you can sit back and relax or take a nap. When we're thinking about using electricity at home and a grid that facilitates customer convenience, we're thinking about energy use that is automated or that can be coordinated with your activity. So maybe, it's enabled through your smartphone, and as you, come home, your home can detect like where your phone is and turn on the heating or the air conditioning right before you get home, for example. So there are a lot of different things that a more advanced clean grid can do to really improve the convenience of customers. I would say a clean grid also ideally would facilitate customer savings, and that could be by right-sizing the system, building out the right level of infrastructure, taking advantage of existing infrastructure as much as we can, And as well as offering real-time information to customers about what's going on the grid. So if there are a lot of low-cost renewable resources and the prices tend to be lower, enabling customers to see those prices and respond to those prices, or providing them with technologies that enable them to take advantage of those prices automatically and thereby the savings, would contribute to that goal. I also think a clean grid would also include clean communities and reduce pollution from cars, trucks, school buses, where people live, as well as reduce pollution from power plants where people also live. And so, you know, in doing so, hopefully equalize a level of environmental quality for everybody, and optimize clean air and clean water as well. So certainly we could do more to ramp up clean technologies like renewables, energy efficiency, and customer demand response, which is, you know, customers' smarter use of energy for compensation. And I would say clean jobs is also amongst that bucket. So, you know, the types of jobs that we're looking at with a clean grid include solar panel installations, wind turbine installations, infrastructure, whether it's like for the transmission system or the distribution system or in people's homes. And so we're getting away from more risky types of jobs like fossil fuel extraction and things like that. So I would say, like, just, you know, to sum that up, we're looking at a low or zero emissions grid and more engaged customers, smarter use of the clean resources that we have, and phasing out the more polluting resources. And we'll need a lot of policy and coordination to figure out how to make all of this happen.
Great. And Gary?
Sure. So to me, a modern clean grid means a grid that, I guess, has certain attributes. One, be smart. So we're continuing to add more intelligence to the grid, make it, you know, self-healing, more responsive. Has to be flexible. One of the big challenges with flexibility is we have very little storage today in our grid. Storage offers all kinds of flexibility because it basically decouples the production of electricity from the consumption. You know, normally you have to match consumption or production with consumption, but storage allows you a little bit of flexibility because it decouples that requirement and gives the grid far more flexibility in terms of operation. I don't know if most people realize that today, probably about 94% of storage for the power grid today is pumped hydro. Fastest growing is battery energy storage, but that's still very, very small compared to the amount of pumped storage hydro that we have, which is, you know, the larger scale storage on the grid. Also, you know, basic blocking and tackling. Grid needs to be reliable, needs to be resilient, needs to be able to respond to storms, cybersecurity attacks, physical attacks, and, you know, maybe not be 100% resistant to those, but certainly be able to isolate and then quickly respond and react whenever those threats do exist. Grid needs to be efficient. This has a couple of different attributes. One attribute is, you know, lower losses, no losses when you move power from the generation source to the end-use load. So you want a grid that's as efficient as possible. But other components also are utilization of equipment or utilization of infrastructure. Today, we're very inefficient at asset utilization. Probably the assets in the grid, which are designed to meet peak demand, means we probably get overall utilization of maybe 50% because that peak demand doesn't occur that often. And as a result of that, we have underutilized resources. The other component of efficiency is also end-use efficiency. We see lighting reducing or becoming more efficient with LED lighting as an example. HVAC systems, heating and cooling systems are becoming more efficient as well. So I think, you know, a clean modern grid needs to be efficient. And then it also needs to be sustainable. You know, there's a lot of work being done today around, carbon free, 100% renewable, net carbon zero. We see a lot of utilities making announcements that by 2050, they want to, some say they want to be 100% renewable generation. I think other utilities are saying they want to be, 100% carbon free, which means they can include nuclear resources and hydro resources in addition to wind and solar. And then other utilities are saying they want to be net carbon zero. But whichever goal is picked, it's moving towards clean energy and moving away from thermal generation, particularly fossil fuel, which is coal and natural gas. So when you look at the big picture, that means changing out about 60% of our generation over the next 30 years to be to reach these goals of 100% renewable. So reducing carbon means, again, moving towards renewable generation. But Jenny also mentioned electrification, and transportation is a big part of that. And forecast from NREL, the National Reliable Energy Lab outside of Denver, is that transportation alone could add 20 to 30% additional grid load over the next 30 years. So the grid needs to be able to accommodate that if we're going to achieve our clean energy goals. And I also agree with Jenny on customer engagement. I think there needs to be more price transparency that customers can respond to and react to, and not take the availability of electricity at one flat price for granted. So I think that's also some changes that we can see going forward with a more intelligent grid, but also a cleaner grid.
Yeah, that's a really good point, and fascinating that you mentioned that. I think electrification is going to be a big challenge in the US going forward. If our electricity demand increases and we are going to switch to these lower carbon energy options, including solar and wind, which are often intermittent, I think it really brings out some of the, I mean, I would like to kind of follow up with you on understanding your opinion. If we're going to integrate larger shares of solar and wind, which require new types of coordination or policy or technologies, perhaps storage, how do you envision the different or the role of the transmission system in terms of integrating these higher shares of solar and wind? Are we prepared to do that?
Do you want me to go first this time?
Sure. Yeah, if you don't mind.
So I think you asked a couple of different questions. So one is, when we look at electrification in particular, and that is a significant potential growth over the next 20, 30 years, we have capacity within the grid and within our generation resources to be able to serve those loads, with one key caveat: avoiding adding load during peak demand periods. So if we can charge electric vehicles during past the evening peak, the early morning hours, or maybe also charge electric vehicles in the middle of the afternoon when there might be excess solar PV available, we should be able to accommodate the electrification of transportation. And so hopefully we can put in either managed charging, whether that's active or passive through rate structure, to be able to shape the demand of electrification so it doesn't increase our evening peak demand, which in most states is what strains the grid. So I think we have a little bit of time. The adoption rate of electric vehicles hasn't been as fast as many have predicted. I think gasoline prices now at around $1.60 probably will slow adoption of electric vehicles since the low price of fuel, but it's going to happen. We're going to see that change. And I think utilities can work incrementally to be able to accommodate the electrification if we avoid peak demand. So utilities look at make ready, which is putting in infrastructure locally to serve charging equipment. And then also from the generation point of view, managed charging becomes important so you avoid peak demand. The other part of your question is the renewables. And renewables have a couple of challenges. One, they're variable resources, so they don't always always be able to produce. The wind doesn't blow 100% of the time, and the sun doesn't shine 100% of the time. But I think the forecasting of those resources has gotten to be pretty accurate. But the challenge is when you do have those resources, you want to be able to use that energy. You don't want to end up in a curtailment situation where you can't use the connected resources to the grid that are renewable. And the challenge with renewables is when those resources are generating, you either have to consume it at the point of where it's, or locally where it's generated. You have to store it. We know there's limited storage on the grid, or you have to move it. And there's limited transmission capacity today to move the energy. And those are really the options. So, you can try and also create demand as well that wasn't there previously. As I mentioned, charging, more electric vehicles to absorb excess solar is the example that everybody points to. And so adding storage is great. Adding transmission also will enable more renewable generation because you can move it to areas where there is load if where you generate doesn't have it. One of the best examples is Texas, where they had a project called CREZ, which I think is a Critical Renewable Energy Zone. And basically the wind generation in Western Texas that was being developed was being curtailed because there was insufficient transmission to move that energy to the cities in the eastern part of Texas. And so they built out the transmission infrastructure, which has enabled them to develop over 20 gigawatts of wind generation in the western part of the state with very little curtailment today as they've added all that additional wind generation. And that's an example of where transmission investment has enabled the integration of renewable generation to the grid.
Jen, thanks. And Jenny, what about these? What about the policy barriers or legal aspects of expanding transmission, as Gary's been describing?
Yeah, so I think there are a lot of barriers, policy barriers to expanding transmission, especially, or more broadly, to integrating higher shares of renewable resources. Because, as we think about how the rules for operating the grid or building out the grid, the power system and the energy system more generally, we've really thought of traditional resources, traditional in the power sector, large traditional power plants. And if we want to incorporate more emissions-free, lower-cost renewable energy resources, we know that wind and solar exists everywhere in the United States, but it's definitely stronger in certain parts of the United States. For example, in the wind in the Midwest and the Great Plains and off the coasts of New England and California. Those are great areas for wind resources. And then for solar, the South does tend to get more sun than the North, but there is solar everywhere. So if we're looking at low cost renewable resources where it's very plentiful, it's not necessarily where people live. So the transmission aspect is a very important aspect of getting the renewables to customers. Transmission is also important for ensuring that the variability in renewables can be evened out. So I think both of these things are things that Gary mentioned, but when you look at a larger geographic area, you're looking at a more diverse supply as well as a more diverse load. You're looking at different time zones. People get home at different times as you go, from the east to the west of the United States. And so the energy usage would be not just one coincident peak, but it would be smoothed out a little bit more. The wind is blowing somewhere, the sun is shining somewhere, of course, unless if it's nighttime. But the transmission system offers a really, it offers like multiple benefits in terms of delivering energy, low-cost renewables to customers, as well as delivering grid flexibility. So I think looking at the policies, certainly there are transmission planning and siting rules that we need to reform. We're having trouble building long line transmission. We're having trouble siting transmission in certain areas. Certainly, we would want to make sure that everyone who has a transmission line through their property is gaining, some benefit, whether it's through adequate compensation or jobs for their community and so on. In terms of market rules, like we do see a lot of these renewables concentrated in certain what we call balancing authorities, so balancing areas where supply and balance and demand is balanced in real time for electricity. And certain regions don't trade with other regions. And so if we really want to ensure that renewable resources are not bottled up in certain regions, certainly sometimes we see negative prices in the middle of the country, whereas other regions don't see low prices. Just getting those low cost resources out to consumers can also depend on how these different regions share electricity and the market rules that govern how they share electricity. I would say also, while we're on the point of infrastructure and getting more renewables online, one thing that I hear a lot from renewables developers is just how long and how costly the process is of interconnecting to the system. And if you're a large power plant and it's taking years, it takes a few years for you to build, maybe an interconnection process of 3 years might be okay for you. But when you start seeing a lot of smaller projects that might want to build in similar areas, and it's taking them, it's taking 3 years, and as more projects are added to the system and need to be studied, there could be delays or could be cost increases. And so we're looking at a bottom-up interconnection process that doesn't really work well for interconnecting a lot of smaller but more numerous projects. So if we can look at if we can think about, okay, how do we come up with a process that really makes sense for renewables? There is some discussion of coming up with a transmission planning process that includes interconnection. So can we look at transmission by thinking about where are the high value renewable energy zones, kind of like the Texas example that Gary mentioned, build transmission out to these zones, and then give developers information about where good places to interconnect are, and just come up with a more organized system of transmitting information to them and identifying places for them to interconnect, rather than relying on them to decide, okay, I'd like to interconnect here, I'm going to apply, we're going to have to go through this study, and that's all going to have to change when we have more projects coming in on the system. So I think those are just 3 areas, trying to get the infrastructure out there to get renewables to customers, to even out the variability, and to interconnect new projects. I think those aspects of transmission planning and policy reform would be very helpful.
Do you think that there's a tension between expanding the transmission system to integrate renewables and looking more at the distribution system as a place to start, where people can generate PV on their rooftops or have aggregated storage through electric vehicles? This is to either of you.
Maybe I can take a first cut at that. So I think that we're going to see both. I don't think it's going to be exclusively, we have to have all of our renewable generation connected to the transmission grid as centralized resources. But I don't think we're going to see everything at grid edge in terms of distributed energy resources. If you look at solar, for example, it's far more expensive to install solar on rooftops than it is to put it into a 10 megawatt solar PV installation where you have economies of scale in terms of your fabrication installation and also managing that system. So I think we're going to see both. distributed resources as well as centralized transmission connected resources. If you look at the forecast, I think Bloomberg New Energy Finance puts the split between smaller scale renewables and I guess utility scale or centralized grid connected resources. About 65, maybe 70% would be centralized or transmission connected utility scale, and then the balance would be commercial and residential rooftop type of renewable generation. When you think about it though, the massive amounts of generation that are going to be retired, trying to replace all of those resources with distributed resources, I think is going to be very difficult, which is why I think we'll see a lot of larger scale because the economics are better. You have a little bit more flexibility in terms of in use when you connect to the transmission grid. You just need to address, the issues that Jenny mentioned in terms of being able to move that energy around based on time of day, type of load, location of where the resources are being generated. One thing that's interesting right now is we're seeing developers being very opportunistic in terms of looking at where coal plants are retiring, and if they can develop renewable resources in the same area, they can tap into the existing transmission grid. For example, the offshore wind project, I think Ocean Wind off the coast of New Jersey, is looking at taking advantage of the transmission resources that are near the coast for Oyster Creek nuclear power plant, which retired. So you can take advantage of transmission, which is being underutilized with the retirement of that plant, and utilize it for, in this case, offshore winds. Once you bring the power back to the mainland, you can tie into a transmission resource. All this renewable generation is going to be tough to do if we can't get the transmission in place. Whether it's getting transmission to the Dakotas for wind, being able to pick up the transmission or pick up the power from offshore wind that's being generated, or being able to move power, through the southern tier where we have a lot of potential solar PV being developed. NREL actually looked at this challenge with their SEAMS project or SEAMS study. The results haven't been released yet in a formal report, but they're available on the grid. And one of the things they looked at is, the movement of energy across the Eastern interconnect with the Western interconnect. We can only move 1.3 gigawatts total interconnection between those two grids today. And that's going to be a limiting factor as we add more renewables, being able to move energy around the country.
Oh, thanks. And yeah, actually now building off of that, there are two new questions that have come up related to the interconnection and transmission system. One is about the how we can address the interconnection process issue. Is it more of a transmission issue, or are there new management practices that can reduce that interconnection time? And Daniel Alberga also commented and asked, there have been several high-profile examples of interstate HVDC projects that have folded in the past few years due to stakeholder opposition. Do you think that a change of approach is required for large-scale transmission to be successfully built out in a timely manner? So I think those are kind of related to interconnection processes and any changes in approach. Jenny, do you have any comments on that, or Gary?
Sure. And just to, go back to earlier question too, I do agree with Gary on a lot of the different points that, on your first question, Noah, that it's not choosing either or distributed energy resources versus, further away renewable resources with transmission. There are benefits to both. They can complement each other, and we'll need both of those types of resources to meet our greenhouse gas reduction goals, at least the international greenhouse gas reduction goals. So certainly the customer-sided distributed energy resources can offer things like flexibility as well as microgridding, as a greater sense of community. For example, the Brooklyn microgrid has local residents exchanging energy, solar energy, on a blockchain platform. And whereas like the centralized system does have a benefit from economies of scale and lower cost. On the two new questions, certainly the interconnection process, there could be new management practices. The one that I mentioned was more of a top-down approach. You know, if you have information about the system, provide that to the developers and do the organization for them rather than the developers trying to build from the bottom up and thinking about, okay, trying to guess at where the good places are to interconnect to the grid. You know, asking the grid operator to do a study of the system and then paying the cost of upgrades. So there could be some new management practices that could reduce interconnection time. In Texas, it does take less time, but not because of the process that I just described, but because they put the onus on interconnecting generators that, you know, if an interconnecting generator has to be curtailed because there isn't sufficient transmission to get their electricity to customers, then that's a risk they face. And so it takes about 9 months to interconnect in Texas, for example. I mean, that could be an alternate way of doing things, but I mean, certainly we would want to investigate a lot of different processes and look at the costs, benefits, challenges of all of those. In terms of the high profile examples of HVDC projects that have folded, I definitely think that a change in approach would be very helpful. Certainly some of the states that don't see a benefit because the project doesn't start or end in their state, if they don't feel like there's a benefit and there's a line going through their state, then, you know, there's a great benefit overall to having that HVDC project in terms of lower cost renewables, enabling certain states to achieve their climate goals. There is room for some negotiation, and there could be, you know, a process where we can enable, you know, everybody to see some of that benefit. So I think there's definitely some way to coordinate and compromise in order to build out transmission, but we really all want to. We have to all come to the table to agree on that one, or see a little bit more leadership from the federal government.
That's a great point. Gary, did you want to explain for those who may not be familiar with HVDC technology a little bit about the opportunities and what it is and how it could, what it means for the transmission system?
Sure. So HVDC, high voltage direct current technology, actually has been around for, I think, 50, 60 years. So it's not a new technology, but basically it's primarily used for long distance overhead transmission lines, and also it can be used for cables, such as if you have offshore wind. So when you look at the long distance overhead lines, the transmission lines themselves are cheaper to build, mainly because if you have a bipolar HVDC line, it only has 2 conductors and not 3, which is typical of an AC line. So your towers are smaller, your right-of-way is narrower. Actually, when you get to scenarios where you're moving large amounts of power, sometimes you have to go to a double circuit AC line, which means you have 6 conductors. You're basically running 2 parallel AC transmission lines. So the amount of space you need in terms of the right-of-way, the towers, the number of conductors, the AC lines themselves are more expensive. Conversely, HVDC requires a converter station at each end of the line. So you have to convert from the AC on the grid to DC, then you can move that power, and then at the other end of the line, you have to invert that back to AC to reconnect to the grid. So the converter station does have a significant amount of cost associated with it. So typically there's a break-even point of moving power point to point using an overhead HVDC line, and that's about 400 miles. So if you're shorter than 400 miles, the cost of the converter stations at each end may not offset the reduced savings of the actual construction of an HVDC line versus an AC line. The other component is losses. There are DC has much lower losses than AC. The converter stations are actually very efficient, high 90% efficiency through the converters, but you don't have the inductive losses which are associated with an AC line. So that's an added benefit for HVDC. But again, point-to-point utilization, for example, bringing power, cheap hydropower from Canada down into New England is an example of where we have an HVDC line in service. Two other applications. I mentioned the interconnect between the Eastern Interconnect and the Western Interconnect. So we have a number of back-to-back HVDC installations. Both balancing areas or system operating areas are at 60 hertz, but they're not synchronized. So in order to be able to move power between the two of them, we convert from AC to DC, cross the border, and then connect back after inverting back to AC. And it's called a back-to-back station. It allows the two areas to be interconnected. So we have a number of those that allow connections, but overall capacity is not that great, as I mentioned. I think it's about 1.3 gigawatts of power. The other benefit of HVDC is in cables. So you can actually move power in large amounts of power. You can move a gigawatt of power through HVDC cables, and you can go long distances without significant losses. Particularly important for offshore wind. If you go more than 30 miles or so offshore, it actually pays to have the converter stations and to use HVDC because of the lower losses. Those losses are primarily due to charging current. If you think of a cable, it's like a long linear capacitor. And with AC, you have charging current, which contributes to the losses. The longer the cable, the higher the losses. And those can be very significant, which is why for long distances with cables, those are normally HVDC. The break even is probably around 30, well, let's say 40 miles in that range. Once you go longer than that, you need to use HVDC. So if we want to bring power, from North Dakota and move that into the Northeast, an overhead line would work if you could get the permitting. You could run a cable too. It might be easier to install from an aesthetic point of view, but it would be more expensive. So those are some of the trade-offs. So again, point-to-point, long distance. We have deployed the technology to move large amounts of power. We also are using cables to move power long distances or for offshore wind, and then we have back-to-back technology. But generally speaking, you need some economic drivers such as high losses in cables or long distances where, again, the cost of construction and also the lower losses make HVDC economically attractive.
Oh yeah, that's a really good point, and thanks for bringing up some more details onto this emerging technology. We've also discussed other technologies like storage, but I wanted to shift the conversation a little bit to the role of software and digitalization. So we've talked about a few different types of hardware innovations, but what is the role of digitalization in terms of integrating higher shares of renewables in a modern grid?
Jenny, do you want to take a first cut at that, or you want me to jump in?
Sure, I could be short, and then I'm sure you have a lot of detailed knowledge on this topic at ABB. So digitalization enables us to leverage technology and the connective network to improve reliability, safety, customer engagement, efficiency, and sustainability of the energy systems. But certainly we have to employ it in a way that makes sense, that enables customers to really benefit from the information that of the state of the grid, of whether we have a lot of renewables online and we've got surplus renewable energy from wind and solar that they can mop up at lower costs to charge their electric vehicles, for example. So there's a tremendous potential to using the grid in a more intelligent fashion through digitalization. and the information that you can make available to customers or the end use devices, the customer devices, which could automatically charge at certain times or automatically operate at certain times when there's a large amount of cheap renewable energy online. So I would say that that's the main role for digitalization, just increasing the convenience of for customers, the flexibility of the system, the efficiency of the system, as well as like the industry has been using it for a long time to monitor the system and improve the safety and reliability of the system as well. I'm sure Gary has a lot more to add to this. So
do we need to be worried about the security or other issues as it becomes more digital?
I think cybersecurity is a major issue for the industry. When I look at digitalization, though, there's really three components. We actually did some study work in this area looking at three main phases related to digitalization for utilities. And the first phase is you take the AL out of digitalization and you get digitization, which is really converting from analog to digital. And the industry has been doing this for a few decades, taking the paper maps in control rooms, putting them into a computer, basically using geographic information systems and digital maps instead of paper maps. So this is something that's been going on to automate and raise the level of digitalization within control rooms. Also digital substations. We're building digital substations where we're using digital sensors in the yard of the substation, or we're converting analog to digital in the yard. And then we just run an Ethernet cable to be able to pull all that information back into the control house with only digital signals. So it's safer, it's cheaper, it's easier to commission, it's easier to maintain, and you can also collect more data for better asset management. And then also, most people are probably familiar with their view of the grid, which is the meter that's on the side of their house. And we now are well into the process of converting those from analog to digital, which then provides customers far more information that they can get rather than a monthly bill, and also gives the utility some options in terms of different types of customer programs because they have the information that's needed to be able to enable it. So digitization is the first stage. Second stage is digitalization. This is really sharing of information. So it's putting together a data lake or data source where all the information that's coming in from different systems can then be shared by the end users, whether it's in the control room, whether it's planning, whether it's customer service, whether it's billing, whether it's operations, balancing, generation versus load. It's really making the most utilization or the most use out of the data that the utility has available. That's really what's advancing level of sophistication, I think, in terms of utility operations. And then the third stage is business transformation. Given that you have all this information, you have all these systems in place, how do you change your operations? I forgot to mention that analytics, artificial intelligence are now appearing on the landscape for utilities. Actually, AI has been around for a long time in terms of load forecasting. Utilities have been doing a great job in terms of the sophistication of their load forecasts using neural networks, and now they're using deeper neural networks to account for renewable generation, which is a little bit more difficult to forecast. Also, analytics are being used for asset performance management, different types of data mining of customer meter data. So all of that's now being deployed and integrated into utility operations. But really the final stage of that digitalization process is how do you change the utility business model? How do you transform the business to take advantage of this? Other factors that get integrated in, everybody talks about the industrial Internet of Things and, the OT, IT, operational technology, information technology, integration, and, the fourth industrial revolution where you now apply computer technology to physical things and devices. So the utility is doing that. You know, when you think of IoT, I think of software. It either controls something or it analyzes data from something, so from a sensor. And so we see that with distribution automation, with substation automation, with various demand response programs. Those are all examples of some software, which is either controlling or analyzing, communications, which are now being deployed. We see field area networks being deployed at utilities, so we have broader reach to devices on the grid. And then the things, the controllable devices, smart devices, and more sensors being deployed on the grid. And I think that's where we see digitalization. Cybersecurity is an issue. I mean, technologies are there to secure the grid, but grids and utilities are constantly challenged from a cybersecurity point of view, and we can't just dismiss that. It's something that's a serious challenge. But a lot of work is being done in that area.
Yeah, that's a great point. So I know there's a lot of students on the call, and one thing that they may be wondering is all of these technologies and algorithms and new softwares are really interesting, but where should they start? If you have any career advice for any of the students, both on the technical and on the policy side, how can people that are interested build skills in this area?
Well, I can go first. Certainly, I know it's a tough time right now. Students are looking for internships and jobs, and the opportunities for paid experiences have been a little bit more difficult to find. But trying to network as much as possible. Right now, we've got webinars, virtual happy hours, see what's available through your schools, but also reach out to alumni networks too, and see if, look for the topics that you're really interested in and that you think could be an interesting career for you, and talk with people in those areas and see if, see how they got there, and just put it out there that you're interested in these fields. And I think some of these strategies might bear fruit in the longer term and also help you better understand the substance as well as the process of potentially starting a career in that field. I want to say that it's tough to reach out, especially during these times when you're not attending conferences and in-person meetings. But I find that most of us in the energy community are very keen on ensuring that the next generation of folks who are working in this space, especially looking to do good, are empowered to do so. And I think generally people have been very helpful. So don't hesitate to ask for help, I think, is the other piece of advice I'd give. Not that I'm necessarily qualified to give advice on behalf of everybody, but I think it doesn't hurt. The worst that can come out of it is that maybe sometimes you have emails that just go unanswered, but folks are busy, so don't take anything like that personally. But yeah, just find as many opportunities like webinars, ask questions, reach out to folks, and sometimes it might be a cold email, and that's okay. But I'm an introvert. I know there are a lot of introverts out there. You kind of have to break out of your shell sometimes, and just really try to learn from talking with more people, and they want to hear from you. So just know that.
So I can add a little bit to what Jenny said. So I'm also an introvert too, but in spite of that, I think one thing that's critically important to any career is networking and communications. You need to be able to communicate, and then the more people that you know and can network with, increases your knowledge base, but it also increases your career opportunities. I think from a broad perspective or a big picture, I think energy is going to see a major transformation over the next 30 years. We're going to see more renewable, more clean energy. It's going to mean significant changes to the power grid and to the generation that we have on the grid today. We're also going to see electrification gain more traction. We're going to see more electric vehicles. We're going to see vehicle to grid. We're going to see second life batteries emerge, reusing the batteries from electric vehicles. So we're going to see a lot of change within the electric utility business, but also energy in general. The digitalization component, applying those technologies to the grid is going to make it smarter, more responsive, more engaging for customers. I think energy is going to be pretty exciting. It's going to be everything from detailed engineering to planning and design to looking at communication technologies and IT. So I think there's a lot of different opportunities. One example I can give you is I do have a 25-year-old son who's working in the energy space. He graduated not from UNC, but from NC State, but he got degrees in mechanical engineering and meteorology. And he's now designing wind farms for NextEra. He's been stuck here the last 4 weeks because he's been working remotely from here rather than holed up in his apartment in Florida. But there's an example of combining two different disciplines in jumping on an opportunity in an emerging field where he's focused on the development of wind energy, and who knows where that's going to take him. But I think there's a lot of different opportunities as we see the energy transformation and we see more clean energy.
Well, thanks, and thanks to both of you for sharing such wisdom and expertise in this area. And I wanted to take the opportunity, we do have a few minutes left. If there are other questions from the audience, please do use the Q&A feature. I'm not seeing too many, but oh. It looks like I don't see any new questions to be asked, but thanks again. Are there any closing messages from the panelists?
Well, thank you for having me. And I really enjoyed the questions, Gary's remarks, your questions, Noah. And it's a really exciting field, as Gary said. So I hope a lot of students are inspired to look into this field. Yeah, that's it. Just stay safe and stay sane. And I hope everyone is doing as okay as you can manage.
So no, thanks for the invite and also for moderating today and keeping us on track with the questions and all of that. Certainly enjoyed Jenny's comments from a policy perspective. I tend to get mired in more of the technical issues and can sometimes lose perspective on the policy side, which I think is equally important. And I think energy is exciting. I think there's tremendous opportunities for students today in the energy field. And when we see, the technologies that are being deployed for the grid and as part of grid modernization, it is creating opportunities for people coming out of school today. And I think that's exciting.
Definitely. Well, thank you all so much. And so I think with that, I hope you all have learned something today. I know I have, and I hope you take that going forward, and hopefully we'll have a more modern and clean grid in the future. So thank you all for attending, and I'll end the session.
Thank you.
Thank you. Bye, everybody.